Hello and welcome to this session on roadmap-based path planning. In this session, we'll be discussing what is a roadmap and how roadmap as a data structure can be used for path planning in known environment. We'll discuss in particular two algorithms, visibility graph-based algorithm and generalized Voronoi diagram-based algorithm that are used as roadmap for path planning. Let us take a simple example to understand how roadmaps can be useful data structure in path planning. Here there is a case where a student takes admission in this college A and the student resides in this building, say B. From B to A, the student explores various routes and finally decides to follow this route. Now, this was possible because there was an entire infrastructure or a roadmap that was available. Similarly, in a known environment, when the robots have to move from one location to another location, some roadmaps or some lanes or routes are created beforehand so that it has not to do calculation or computation online when it starts to plan its path. Recall that in unknown environment we use algorithms like bug algorithm because there is no information about the geometry of the obstacles. But now the environment is known. You know the geometry of all the objects and obstacles. Then you can plan the paths beforehand. So obstacles can be static or dynamic. Think of a scenario where we have a shop floor in which 2-3 robots move every day to perform their tasks. So they may be going from one location to another location which are known. And there can be machines, there can be furniture, and location, the geometry of each and every object and obstacle is known in this. So for such a workspace having, say, static obstacles, one can plan paths between every pair of points beforehand so that at the time of any online path planning, one of the paths which is the shortest path as per the requirement can be chosen. So this is known as a two-stage path planning where you first create all possible paths and in the query stage you look at the starting and the destination position and you choose a suitable path between these two positions. Roadmaps are useful when many paths are to be constructed and used in the same environment again and again. So what we do is that we construct a roadmap, that is the connectivity between different locations, and store them in a data structure called a roadmap. There are many roadmap-based approaches. They primarily fall into three categories. One is a purely topological model where every location is represented by a node, and between any two locations, if there is a connectivity, there is a path, then that is represented by an edge. For example, here 5 and 6 are directly connected, whereas to approach 4, 5, from 5 one has to go either via 2 or 3. So here the topological aspect of the environment is considered. That is known as a topological model. The second one is a geometrical model where the environment, the entire geometry of all the obstacles, everything is considered, taken into account. And then we create the free space which is not containing any obstacle. As you know that free space is the collection of all configurations which are free configuration, they are not colliding with the obstacles. In the free space, we create the roadmap. The third type of approach is a grid-based approach, which is also very popular, where the entire environment is divided into cells or a grid, and each cell of the grid, how that is connected to another cell of the grid is found out. Accordingly, roadmaps are created. I now define formally what is a roadmap. So a union of one-dimensional curves in the environment is a roadmap if for all starting positions q and the goal positions G that can be connected by a path. That means there is a connectivity between these two. Three important properties hold. First of them is accessibility. That means there exists a path from Q to some point Q prime on R. By this we mean that suppose you have a point, say Q, which is not on the roadmap, and here is the roadmap. Here is the roadmap, and in this roadmap I have a point, say Q prime. So this is point Q, and this point is Q prime. I'm choosing this point, and we can find out a path between Q and Q prime, and then that is known as the accessibility. Then we have departability. There exists a path from G prime on R, the roadmap, to G. Suppose your exit point or the destination point is this, and we have to find out whether this destination point is connected to the roadmap through a path or not. So let me take this destination, and there is a path. So if there is a path from the destination to the roadmap, and there is a path from the start position to the roadmap that can connect this Q to the roadmap and this G to the roadmap, then accessibility and departability are satisfied. What is the third property here? That is the connectivity. There exists a path in R, in the roadmap, between Q prime. This is Q prime. Let me choose another color. This is Q prime to G prime. So let this be G prime. So between Q prime and G prime, if I can find a path, then you can start from Q, go to the roadmap. On the roadmap, you have already a predefined path, and then from G prime, you can go to the destination position G. If these three properties are satisfied, I call this union of curves as a roadmap. Here is an example showing a roadmap. So this is the point which is the starting point. That is, you can call it Q. And this point which is shown is Q prime. Then you have a destination point, as you can see here, this destination point. And then it can be connected to the roadmap, which is a black curve, union of various curves. And then we can find out a path between the starting position Q prime on the roadmap to the end position G prime on the roadmap. And from G prime we reach G. This is known as a roadmap. There are well-known methods for constructing roadmaps. Some of them depend on visibility graph. The others are based on generalized Voronoi diagram, and there are a couple of other methods too. In fact, plenty of methods are there. We'll be discussing today these two methods based on visibility graph and generalized Voronoi diagram. We first understand what is a visibility graph. It is a graph of intervisible locations for a set of locations and obstacles. So every location is represented by a node, and between two locations, if there is a visibility, then that is represented by an edge. Consider here an environment having these two obstacles shown here. If a robot is standing at this position, you can see that it can view or have visibility in all the directions except possibly some of the directions which are obstructed by these two obstacles. So if I look at this line, everything is visible. But if I go beyond this line in this direction, visibility will be shortened. Similarly, if I take this line, then the all the objects or every other location falling on this line is visible. But any location which is somewhere here will not be visible from this location, the starting location. So this way we can see that there can be points which are not visible from a given location. And if we choose another location, for example, I choose this location. From this location, this is visible, but a point which is here, this is not directly visible. So to reach this point, we will have to take a collection of points which are visible to reach the destination. So for example, reaching from here, you will pick up the first visible point, and then from this location, you will update the points of visibility to reach this destination. Visibility graph is based on this principle that given a point, start point and goal point, we look for all the vertices of obstacles present in the environment which are visible from the given start location. And then through those vertices, we traverse to reach the destination, making a shortest path. In order to make a visibility graph, all edges joining any two vertices of the obstacles which lie in the free space are constructed. So here you can see that these are a pair of vertices. In this way, we can keep on joining any pair of vertices and can make the visibility graph. You can see that this line, which is a dashed line, is not the right or valid edge because it is passing through part of an interior of an obstacle. So all edges which are only in free space are considered for constructing the visibility graph. This is an example of a visibility graph shown by blue dashed line from a start position to a goal position shown here. This is the starting and the goal position. There are only three obstacles here, yet the visibility graph is a little complex. Now think of a scenario where we have, say, hundreds of different obstacles like in autonomous driving, and then you have to create a visibility graph on a real road map. The question is, how do we handle this? So the visibility graph becomes very complex, highly complex, when the number of obstacles is high. And therefore, we reduce the complexity of the visibility graph, making use of only supporting line and separating line. A reduced visibility graph consists of very few edges as opposed to the original graph, as you can see here. These are supporting and separating lines. Lines shown here by red are separating lines, and lines shown by green color are supporting line. What is a supporting line? Let us see. Suppose you have an obstacle given here and another obstacle which is given here. This is obstacle 1 and 2. Consider this edge which is joining these two vertices. Now this edge is, if we extend this edge to both the directions infinitely, you can see that obstacle 2 is in one region and obstacle 1 is in another region, separated by the extended line made by this edge. So if the obstacles are in opposite region or different regions, when the supporting edge is extended infinitely to both the sides, then this is known as a separating line. I consider the example of a supporting line now. So I have got obstacle 1 which is shown here, and then I have got another obstacle, say given like this. In this case, we have these two vertices. These two vertices, if they're added, they're joined, and think of a line which is extended on both the directions. So this edge which is falling on this line, infinite line, is dividing the entire region into two parts again, but both the obstacles 1 and 2 fall on the same side of the line. This is known as a supporting line. So reduced visibility graphs are consisting of only those lines which are supporting line or separating lines. You can see that the two examples shown here are neither the supporting lines nor separating line edges, because when we extend them, then they are cutting the obstacles. That means they are not dividing the obstacles in two regions. They are actually going through the obstacles. So they are not supporting or separating lines. These lines are avoided in constructing reduced visibility graphs. Rotational plane sweep algorithm is one of the most celebrated algorithms used in visibility graph-based path planning. To understand how the algorithm works, let us consider the scenario having three obstacles as shown here using gray color objects, and let the robot be placed at this location shown in the center by a red dot. Let us assume that the robot is equipped with an infinite range sensor and it is rotating its sensor in all the directions through 360 degrees. Starting with the direction in which it is viewing, let this be the line of sight of the robot currently. When we move in this direction, rotate in this direction, there will be a point or a direction when you will find that the line of sight hits this obstacle vertex. Let me call it A. Now at this point, we can see that if we move further, if we rotate further, then at any other position, the line segments or the edges AB and AC will be intersecting with the line of sight. That means these are obstructing the line of sight because of the obstacle present here. So I can say that A is the starting point of the edges AB and AC, which are obstructing the line of sight. As we move further and rotate the ranged sensor, then there will be a point when this line of sight will be intersecting the point C or the vertex C. Now at this point you can see that the edge AC will be no longer obstructing or intersecting with the visibility line or line of sight. Therefore, if we look at the active edges which are responsible for having obstruction in the line of sight, will be only having AB and also CD, as you can see, these two lines, AB and CD. Why? Because if we move further, then CD will start obstructing. So in this way, in rotational plane sweep algorithm, what we do is that we move the sensor in all the directions through an angle of 360 degree and look for the vertices of those obstacles which are hitting the line of sight, and those vertices will be such that there will be some edges incident on those vertices, and those edges will be responsible for obstructing the visibility of the object or the robot. In this way, we will be able to find out all those vertices which are visible from the current location. So for example, this vertex is a visible vertex B from the current location. You also have found out that this is a visible vertex. And if we move further, there'll be a point when this vertex is visible, but if we move beyond this, then the edges, if I call this as E, F, and G, then EG and EF will be the edges which will be intersecting with the line of sight, and hence there will be an obstruction. So E will be the starting point of these edges, EG and EF, for obstructing the vision. And at the same time, when I go further, at this point, EF will be no longer obstructing the vision, but FG, you can see, will start obstructing the vision. So in this way, what we do is that we keep on updating those edges which are intersecting with the line of sight as active edges responsible for obstructing the vision, and at the same time these vertices are also counted which are visible from the current location, like the vertex E is visible from the current location, but F is not visible, because you can see that these two are lines which are responsible for its obstruction. So this line is falling before F, and therefore F is not visible. Let me again repeat that this line EG is falling before F at a distance which is less than the distance between the current location and F, and therefore F is not visible. In this way, what we do is that we look for all points on the obstacle which are vertices of the obstacle that are visible from the current location, and we keep on moving towards those vertices which are closer to the goal of the object. In this way, visibility graph is constructed. I now introduce rotational plane sweep algorithm step by step. So input here is a set of vertices Vi of the obstacles and the vertex V, which is the current location from where we are looking for visibility. Output will be a set of vertices from that list Vi, which are visible from V. That means which are in the line of sight of V. So this is a scenario where we have two obstacles, and each of these obstacles is having four edges, and the current location is V. VV prime is the horizontal line where we have the current line of sight. For each vertex Vi, we calculate the angle alpha I, the angle from the horizontal axis to the line segment VVI. So for example, for V3, we are calculating the angle between VV3 and VV prime, the horizontal line. And this is the minimum angle because we compute angle in the counterclockwise direction. Create the vertex list E containing alpha i's in the increasing order. So in this case, V3, V7, V4, V8, V1, V5, V2, V6 will be a sorted list of vertices with increasing angles. Next, we have to construct an active edge list that is obstructing the line of sight. So starting with the horizontal line which is shown here, VV prime, we will be considering all those edges of the obstacles which are hitting the line of sight. So in this case, E4, that is V1, V4, E2, that is V2, V3, E8, that is V5, V8, and E6, that is V6, V7, are initially put in the active list S. So S is created. Then after that, starting with alpha 3, or for all values of I, starting from the smallest angle for all I, if VI is visible to V, then add the edge VVI to the visibility graph. So this is the first step to creating visibility graph. Let us see, in case of V3, we can see that V3 is not visible from V. Because it is not visible from V, therefore we will not be adding V3 to the visibility graph. Now, but you can see that similarly for V7 also it is not visible, but V4 and V8 are visible. So definitely they will be put in the visibility graph, like VV4 and VV8 are two edges that will be kept in the visibility graph. Next, if Vi is the beginning of an edge E not in S, then we will insert this edge E into S. In case of V3, you can see that V3 is the point from where E3 begins. So if we are moving in the counterclockwise direction, rotating in the counterclockwise direction, you can see that at this line of sight, which is overlapping with VV3, it is in the same direction as VV3, E3 will be the next edge which will be blocking the line of sight, and therefore E3 has to be added into active edge list S. On the other hand, if Vi is the end of an edge in S, then we delete the edge from S. So if you remember, initially we have the edge list S is containing E4, E2, E8 and E6. This is the initial edge list, E6. Now we find that at this point V3, when we are reaching at the line of sight which is coinciding with VV3, E2 is the line, E2 is the edge for which V3 is the end point. So it is written, if Vi is the end of an edge in S, which is already in S, then delete the edge from S. So we will be deleting the edge E2 because it is not going to obstruct the line of sight any further. At the same time, the next edge is E3, which is going to be obstructing the line of sight in future when we further rotate the line of sight. And therefore, E3 has to be added in the updated active edge list. So this is what this says, that we will keep on adding and deleting edges in the active edge list, in the sense that those edges which are obstructing the line of sight or are intersecting with the line of sight, they will be added, and those which are not going to intersect or overlap with the line of sight in future will be removed from the active edge list. Let us trace this algorithm for this scenario where we have these two obstacles. We first of all find out vertex list as we have done before. Then we find out the active edge list S, which is E4, E2, E8, E6. Now at alpha 3, when you have V3 vertex, the active edge list will be E4, E3, E8, E6 as we discussed before. Next vertex is V7 in the increasing order of angle. And here you can see that now E6 is dropped from the active edge list, whereas E7 enters. Next we come to V4. You can see that V4 is visible from V, and therefore VV4 will be added in the visibility graph, and hence our visibility graph starts to grow. You can also see that V4 is the endpoint vertex for E3 and E4 edges, and therefore from the active edge list, both these edges E3 and E4 have been removed. So what remains is only E8, E7. Similarly for V8, you can see that now V8 is the endpoint of E7 in E8 edges, and therefore both these edges are discarded from S active edge list. At the same time, VV8 is added because V8 is visible vertex. Rotating further in anti-clockwise direction, we reach V1, and V1 is also visible from V, and therefore VV1 is added in the visibility graph. So now you have three edges in the visibility graph. At the same time, you can see that V1 is the starting point for these two edges E4 and E1, because if we rotate further in the anti-clockwise direction, E1 and E4 will begin to obstruct the line of sight. Similarly, we process V5, V2 and V6. Finally, the visibility graph from V contains these three edges VV1, VV8 and VV4. In this way, we move ahead and find out visibility edges from each of the vertices and location. Let us consider this example where we have to plan a path between a starting point shown here to a goal point which is shown here. We have three obstacles and these lines are showing visibility lines or lines of sights in different angles starting from the horizontal line. First, we will be constructing the visibility graph. That means all the edges which are in the reduced visibility graph as we discussed before. And then we will create a shortest path between the start and the goal point. So we sweep a line originating at each vertex. We record those lines that end at a visible vertex of obstacle. In this way, you can construct a visibility graph as shown here by black lines. And then from the Q start, that is the starting position, to the Q end, that is end position, we can find out the shortest path by using any standard method of shortest path finding. If there are n number of vertices in the given environment, let us look at what is the complexity of the algorithm. So if we apply a purely naive approach where every pair of vertices is compared, then you will be having n into n minus 1 vertices computation. Then these pair of vertices will be checked against the edges which are present. So overall you will have big O n cube computations required for a naive approach. But if we use a sweep line algorithm or the rotational plane sweep algorithm we discussed right now, using a binary search tree as the data structure for storing information, then this gives us big O n square log n, and a more optimal solution is to the order of big O n square. Visibility graph is a simple method, but you can see that shortest paths that we compute try to stay as close as possible to obstacles, so which is quite dangerous because any execution error will lead to a collision. That execution error can be caused by, say, a motor malfunctioning, or it can be because of the frictions or any other reason, that if there is a small deviation, it may hit the obstacle. It becomes more complicated in higher dimensions. If we even consider visibility graphs in three-dimensional scenario, then it becomes very highly complex. So safety is more important than finding out a strictly optimal path in many scenarios. Not hitting the obstacles is very important. Voronoi diagrams are another rich structures which are used in roadmap construction. To understand what is a Voronoi diagram, let us consider 2 points. These are two locations in the plane. And imagine all those points which are closer to A than B, and all those points which are closer to B than A. In case of 3 points, also we will see how this is done. So these are 2 points shown here, point A and point B. We join them with the help of a straight line segment and draw a perpendicular bisector on this line, as is shown here. This is the perpendicular bisector, imagine. Then we know that any point which is falling on this line segment is at equidistant from both the points. Or if I choose any point which is here at this side of the line, which is the perpendicular bisector, then this point will be closer to A than to B. Similarly, if I choose a point here, then in this case B is closer than A. That means this perpendicular bisector has divided the entire plane into two regions. Region 1, where we have points for which B is closer than A, and region 2, where we have points where A is closer to those points than B. This is known as the simplest Voronoi diagram. Coming to 3 points, we have 3 points shown here, A, B and C. So we pairwise join them and draw perpendicular bisectors as is shown here. Now if I consider, and you know that these points, these three perpendicular bisectors will be meeting at a point. If I choose a point here, you know that this point will be closer to B, or B will be closer to this point than A, and B will also be closer to this point than C because of the regions that we have already created. Therefore, any point in this region is closer to B, or in other words, we can say that B is the closest location than A or C for any point belonging to this region shown here. Similarly, for A, we have this region for which we can say that A is the closest location, and any point similarly belonging to this region, C will be the closest location. This is a simplest Voronoi diagram. If we have more points, then in a similar way, an iterative way, we can proceed to construct the Voronoi diagram. This is an example of a Voronoi diagram, and having several vertices, as you can see, and each region in which a vertex belongs or a location belongs, that region is containing all those points which are closest to this point vertex than any other point. So for example, if I consider this point, then this region is such that any point in this region will have distance smaller from this vertex than any other vertex in the plane. Complexity of the algorithm, if we look at the Voronoi diagram construction algorithm, is big O n log n in time and big O n in space. This complexity is important because we will be using Voronoi diagram as the data structure for construction of roadmap. So for construction of roadmaps, let us consider that these points are obstacles in the given environment. That environment can be, for example, a roadmap construction environment for autonomous driving, or it can be a shop floor in a factory. So these are obstacles. Idea is to construct a safe road map so that none of the obstacles are collided with the robot. You can see that if I start from this location, which is shown here, say A, and if I have to go to a location, say B, this location B, in order to go from A to B, where these obstacles are static in nature, we would like to have a construction or a road map made beforehand so that we can find out which is the shortest path. So when I move along these edges of the Voronoi diagram, these edges give me a safe distance from both the obstacles. In fact, these edges are at equal distance from both the obstacles. And if there are more than two obstacles, then it is at equal distance from all the three obstacles or any number of obstacles. So in this way, I can find out a shortest path in this road map, and therefore all roadmap based path planning requires construction of roadmap beforehand, and whenever there is a query of finding out a path from A to B, I can use that roadmap to construct a shortest path. Generalized Voronoi diagrams are extended version of the Voronoi diagram where the obstacles or the locations need not be simply a point. You can have arbitrary shaped regions as is shown here. So we have three obstacles, A, B, and C. And we have to construct a path or a roadmap in this environment where if I take a point moving on this roadmap, then it should be at equal distance or at a safe distance from all the obstacles. So you can see that here in this environment, the boundaries are also considered as obstacle. So starting from this location, if I move, you can see that any point on this line segment is at equal distance from both the boundaries. And so, in the same way, we find out that any point which is at the equal distance, at a equal distance from two nearby obstacle, the locus of all those points is considered to be generalized Voronoi diagram. So let there be n obstacles. The locus of points which are at equal distance from any two closest obstacles is called a Voronoi diagram. Key property is that the points on the edges of the Voronoi diagrams are farthest from the obstacles in the range. This is another example of a Voronoi diagram where these blue points are those points like A, B, C, D, L, those you can see. These are the points where we have three or more obstacles nearby, and these are the points which are at equal distance from all nearby obstacles. So for example, L here, you can see that this L is having three nearby obstacles. Uh, One is this obstacle, the second is this, and the third is this. So these red shaped objects are obstacles, and Voronoi diagrams are constructed like this. Once a roadmap is constructed using Voronoi diagram, as I told before, you have to find out a path from one location, that is Q start, to another location, that is Q goal. So we find a point Q star start on the roadmap. It is this point. This point is Q start star. And also we find out another point, that is Q star goal. So this point Q star goal is somewhere here. So you can see that this is Q star goal. And once we have found out 2 points which are closer to Q star and Q goal respectively, from Q star start to Q star goal, we will find out a shortest path as is shown here through this red curve. And then we take the union of these three curves. One curve is the straight line from Q start to Q star start. Another straight line from Q star goal to Q goal. And then this red curve which is shown here. That is the shortest path from Q start to Q goal. Voronoi diagrams are very good, but they are difficult to compute in higher dimension or for non-polygonal obstacles. So for non-polygonal obstacles, we generally bound them into polygonal boundaries. That is, we find out polygonal approximation of those boundaries, and accordingly we create Voronoi diagram. Then we have approximation algorithms which exist. But use of Voronoi graph is not necessarily the best heuristic. That is, a stay away from obstacle can lead to paths that are very conservative. If we are expecting that we should be at equal distance from two nearby obstacles, then this is such a conservative path that if my robot moves in a slightly deviated path, then it may be showing some errors where it is actually not an error. Roadmap-based path planning process is a two-stage method. In the first stage, which is known as the learning phase, roadmap is built like a visibility graph or a generalized Voronoi diagram or a Voronoi diagram is constructed. In the second phase, when you have actual query to find out a path from one point to another point, then user-defined query is generated, and accordingly you create a shortest path or a path which is suitable. A corridor map method takes care of the point that generalized Voronoi diagrams are too restrictive, and therefore first in the construction phase we create a corridor instead of just a roadmap. And then in the query phase, a user-defined query path is generated, which is within the corridor. By corridor, I mean all safe locations around the roadmap. Corridors are generated by first considering the road maps as backbone path. And then around that backbone path, all the safe locations, by looking at the geometry of the robot, all the safe locations are found out, and robot can be made to be moving in within the corridor. So you can see that if there is a disc shaped robot, then the corridor map on the right side of this figure, you can see that the corridor is represented by the cyan color. All these directions are safe directions. Main advantages of corridor map method are like free space is utilized to plan paths. You have more flexibility. Corridors can be constructed using any method, any of the methods like a visibility graph or a generalized Voronoi diagram or a sampling based